Hey, this is Mr. Beckstrom, and today I wanted to go over a sample problem from section 2.1. This is number 6 in the homework, or a problem just like number 6 in the homework. And here what we're trying to do is we're trying to come up with a method to approximate the slope of a tangent line at a particular point on a curve. So before I get into the exact problem, I just kind of want to take a conceptual look at what we're trying to do here. So we're trying to find the actual slope at the value x is equal to 2. So let's say I have the, let's say I have the point x equals 1 here and the point x equals 2 there. And I have some curve, it looks like this, right? And the curve is smooth, which means it's continuous and differentiable and all that good stuff. And here's the value on the curve right here, where x is equal to 2, and we get a better line than that. And the tangent line is the line that comes through and just touches the point on the curve right there, and no other points anywhere locally, anywhere close to that point. So that's the tangent line there. And we want to know the slope of that tangent line. So we're talking about rise over run. At this point, unless you've taken a calculus class before, we don't have a good formula for this. We can't just eyeball it and give an exact slope. So we're going to use some methods to try to approximate it at first, and this is one of our methods. Put that back in the camera here. Oops. So the first thing I'm going to try to do, and this is what this problem is talking about, is we can use the points slope formulas to look at the slopes of secant lines that are close to this tangent line, and we can get secant lines that get closer and closer to the slope of this tangent line. So what they're asking us to do is first take a look at the secant line that goes through the x values of 1 and 2. So here's 1 and here's 2. Change color of my pen. So if I were to look at those 2 points, it would be this point here and that same point. If I were to draw a secant line, that's a line that goes through both of those points, it would look something like this. So you can see that the slope of this line and the slope of our tangent line are very different, not too similar. So if we got that, it's not going to be real close, but it's going to be, maybe somewhat there. But then we're going to go closer, and we're going to keep the same x value of 2, but now instead of 1, we're going to look at 1.5. So we're going to go into 1.5. Now we're going to look at this point and the 2. And notice that we should be getting that line. We should start to be getting a little bit closer to the align with the slope of our tangent line. And as we move this point to the right and get closer and closer and closer to our tangent line, we'll see that the slope of the secant line is going to eventually, if we kind of get infinitely close, it's going to eventually become the same line as our tangent line. So we can, if we get close enough, like it is here, we can eventually come up with what's called a conjecture, or a good guess of what the slope of that tangent line is going to be. All right, so that's kind of the idea, the concept of this. So let's go ahead and do the math part of this. So what it's trying us, or what they want us to do the first time here, is go ahead and find the slopes of all of these secant lines. So in order to find the slope of any line, we need to know the formula for that. So the slope of a line, which we'll call m, that's going to be equal to the y2 minus y1 all over x2 minus x1. x2 minus x1. And that's simply if you just have 2 points you take the y value from the second point minus the y value from the first point, all divided by the x value from the second point times the x value from the first point. So for all of these, we're going to have the x value from the second point and the x value from the first point. So the bottom is done. And to find the top, all we got to do is put those x values in the function here, and that will spit out the corresponding y value. So if we put the x1 in this function, it'll spit out our y1, and if we put the x2 in this function, it'll spit out our y2. So for this first one here, so we'll call that M1. M1, we're going to have on the bottom, we're going to have 2 minus 1 on the bottom. So 2 minus 1 on the bottom, because that's my x2 and that's my x1. And on the top, what I'm going to do is I'm going to go ahead and use my calculator. Let's do it there. And turn that on. All right, hopefully we can all see that. And what I'm going to do is kind of make this a little bit easier. I am going to put this equation, the negative 4x squared, in my y1. So you hit y equals. And then you're going to do negative 4x squared. Enter. Now I can pretty easily pull that up. And I'm going to go ahead and use my table so I can get those values pretty easily. And I'm going to go ahead and make sure that my table set, that's a second window, has the independent variable should say ask, and the dependent variable should say auto. That way I can put in an X and it'll spit me out a Y. So mine's already set, and then I go to second graph, which is my table. And I'm going to go ahead and just put all of these values in. So I know I'm going to be using 2. So that gives me a negative 16. And then I'm going to be using all of those values. So 1, 1.5, 1.9, 1.99, 1.999. All right, so those are going to be all of my corresponding y values for each one of these x values here. All right, so let's go ahead and do these. So for this first one here, 2 corresponds to negative 16. Negative 16, and I'm going to keep that calculator on my other screen so I can see it. And that's going to be minus, and the 1 corresponds to negative 4. Negative 4. And if I put this in my calculator, so negative 16 plus 4 is negative 12 over 1 is negative 12. So that should be my slope for this line here, so negative 12. So I know it doesn't correspond to this one right here. This is just kind of an arbitrary graph. And when we're done, I'm going to put this actual graph in there, and then we'll see what that slope looks like. All right, for the second point here, so for M2, we'll call that one M2. So on the bottom, we're going to have 2 minus 1.5. And on the top, we'll still have the negative 16, because that goes with our 2, minus, and then the negative 1.5, and I'm looking at my calculator, corresponds with negative 9. So minus negative 9. And if you put this in your calculator, you should get negative 14. All right, and then M3. So on the bottom, you're going to have 2 minus 1.9. And then negative 16 minus, and you're going to put the sure that minus is good. You're going to put the 1.9 in your calculator, which gives you a negative 14.44. Negative 14.44. Kind of running out of room here. Sure, that's a big negative here. And that's going to be, what am I at? 1.9. That's going to be negative 15.6. Negative 15.6. All right. And let me give myself a little more room here. So M4. So on the bottom, I'm going to have 2 minus 1.99. 1.99. And this one might be cut a little bit short in my table, so if it is rounded, just make sure you use the whole number there. And on the top, we're going to have 2 goes with negative 16 minus, and the negative 1.99, excuse me, goes with negative 15. Excuse me, negative 1.99 goes with negative 15.84. Negative 15.84. That's when we plug in that 1.99. And then you should get something around negative 15.96. Negative 15.96. And finally, I'm not going to put that whole thing in there. You should hopefully get the point, and the final thing should be negative 15.996. All right, so negative 14, negative 15.6, negative 15.96, negative 15.996, and what would our conjecture be for what the actual slope is when we finally get to 2? I think we can probably see it looks like it's going to be negative 16, because it looks like we're getting closer and closer to negative 16. So that would be your answer for this one, and the others are going to be similar. All right, that's it. If you have any questions, let me know, and I hope you have a great rest of your week. Thanks.